The next type of function that we're going to review is an exponential function. So the first thing we want to look at is what exactly is an exponential function and how do we recognize that as a situation as exponential. The table shows the growth of $100 invested in 1996 at an interest rate of 5.5% compounded annually. So in 1996, we had $100. And in 1997, the interest earned was $5.50. And then in 1998, we have an increase of 5.8. And in 1999, we have an increase of $6.12. And in 2000, we had an increase of $6.46. So what we see is that the amount that you have is increasing, but it is not increasing at a constant rate. When we have a linear situation, we have a function that increases at a constant rate. When we have an exponential function, we have a function that is increasing by a fixed percentage. That's the definition of exponential, when it's increasing by a fixed percentage. So the function looks like this, and this should look familiar to you. And we had $100 as our initial amount, and the interest was 5.5%. So 1 plus 5.5% would be 1.055 to the t power. So this is the function we have dealing with here. So it's just important that we recognize, and you're going to be tested on this, the difference between when is something increasing at a constant rate or decreasing at a constant rate, and then when is something increasing or decreasing by either an increasing rate or a decreasing rate. That's going to become a big deal in calculus. So exponential functions are either increasing at an increasing rate, usually if they're increasing, or at a decreasing rate, and just by a fixed percentage. So it's important that they notice the difference between the two. So let a be a positive real number other than 1. The function f of x equals a to the x is the exponential function with base a. So that's straight from the textbook. That's the definition of an exponential function. F of x is equal to a to the x. And so what we know about exponential functions is that the domain of all exponential functions are all the reals. So I have all the numbers from negative infinity to infinity. And if my function is just f of x is equal to a to the x power, the range is going to be from 0 to infinity, greater than 0. And not greater than or equal to, because we remember that exponential functions have an asymptote. And the range always depends on where the asymptote is. We remember we have y equals a 1 plus r to the t power. We also remember that in exponential functions, we deal with the a-pert formula a lot. That's going to come up. So when would the function represent exponential growth, and when would it represent decay? Well, it depends on the base. Your base is in between 0 and 1. Then we're going to have decay. And if your base is bigger than 1, then we have what's called exponential growth. What about if I have a base E formula, a base E exponential formula? Then it depends on the exponent. So something like y equals 5e to the 2x would be a growth function, or something like y is equal to 2e to the negative x would represent a decay function. So if my exponent's positive, we have growth. If my exponent is negative, we have decay. So that's just a review of exponential functions, a quick review. Those are the two that we see the most. We know exponential is increasing by a fixed percent. Exponential functions have a horizontal, I should add that, have a horizontal asymptote. And notice I'm talking kind of fast and I'm going kind of quickly. These are all the things that I'm expecting that you know, and I'm just reminding you of. Okay, so exponential functions also have something called concavity. Concavity is when a graph bends, curves. When it curves, basically, curves or bends upward or downward. And so when we have a graph that bends upward like this or like this, we say that is concave up. And when the graph bends downward like this or like this, we say that is concave down. I think we probably remember that. And so what happens with concavity is the concavity is going to tell us that it is not just increasing or decreasing, but what is the rate at which our graphs are increasing or decreasing. And we're going to get to that pretty soon. Okay, so something that we might need to remember is how to graph this function. I'm not too concerned about you knowing how to graph. I'm more concerned that you know that this 2 represents the initial amount. It's a growth function. This -4, this is we have exponential growth here. This -4 right here, this -4 tells me that my graph has been shifted down 4. So the horizontal asymptote for this graph is horizontal, so it's y equals -4. The domain of this graph, the domain for all exponential functions, or is all the reals, so we can write -infinity to infinity, and the range depends on the asymptote. Remember, the range depends on the asymptote. So if we have a growth function, it's going to do something like this. We've got a horizontal asymptote at y equals -4. And let's see if we can figure out what the y-intercept is. If we plug in 0 for x, we get 3 to the 0 is 1, 1 times 2 is 2, and 2 minus 4 is -2. So we've got a y-intercept at -2. And it's going to curve up like this and approach the asymptote to the left. So we know that the range of this graph depends on the asymptote. And so if the asymptote is at y equals -4, then the graph will stay above -4. So it's from -4 to infinity, not including -4, remember, because an asymptote is a line, imaginary line that the graph approaches but doesn't touch or cross. So we're not going to include -4. The next thing we want to do is we want to know how to find zeros. Graphically and algebraically. So we're going to look at both ways. This little x right here belongs down here. So we'll move that. So let's algebraically find the zeros first. Remember a zero is defined as the x when y is 0. So we're going to plug in 0 for y, and we're going to remember how to solve for x algebraically. So the first thing I want to do is add 2.5 to the x power to both sides.